All right, everyone, welcome back. I hope you enjoyed the last week with the Thanksgiving and whatnot. So in the rest of the course, so we have two lectures, one today and then one next week. We're going to have guest lectures. Today, we have Aishwarya, who is a PhD student at NYU. She's been here for about 3 years now. Third year. All right, so please do meet yourselves. I mean, it's like almost the end of the semester already, right? So you should know how to use Zoom. Anyway, Aishwarya is in her third year of PhD study. Then she actually has experience working at a company and also doing research while doing her master's program at UMass Amherst. And then since she joined NYU, she's been looking into various problems, but one main theme that she has always stuck to is how to build a machine learning system that's going to handle not just single modalities, but the multiple modalities or the sensory input modalities. Now, why is there an important thing? Aishwarya is going to tell you a lot about it. But one thing I want to just add to that is that the language turned out to be the latest and the very recent invention of evolution. Before that, evolution spent tons of, if not the millions of years, trying to come up with the various sensory organs, right? Starting with how to see the word, how to hear the word, how to sense the word, and so on. So that actually tells us that a lot of, let's say, what we call intelligence must be captured by the sensory perception that is beyond language. So, well, but I think I'm going to let Aishwarya tell you all about it. Now, I want this to be as interactive as possible. It's not every day you get to talk to the third year PhD students who are actually doing some research, and like the professors who just slack off, right? So if you have any questions, do ask Aishwarya as much as you can. And then Aishwarya, the floor is all yours.
Thank you. Thanks for the introduction. Like Cho said, I'm like 2.5, so third year now, PhD student working with Cho as well as Yan. I've mostly worked on multimodal machine learning and a bit of like transfer learning and NLP, but this is what I'm going to be talking about today. And please feel free to stop me at any time. I've been told I speak really fast, so just I'm going to try and speak slowly, but if I forget, please let me know and I will slow down. Okay, so let's start. So this is what I have planned for today. Beginning is with tasks and data sets. I'll also motivate why multimodal machine learning before that, but in general, first the tasks and data sets, then some of the early influential approaches, because prior to the crazy transformer revolution, which I'm sure you heard a lot about in the NLP class, given that that's what we do right now for all NLP tasks. Before that there were a few influential approaches, so I'm gonna speak about that briefly, and then switch to the more recent trend of using multimodal transformers. And then I'm going to talk a bit about my own work, which was accepted to a conference this year, and then finally end with some limitations in general of the models that we have now and some future directions, which could be interesting to work on if you're interested in this area once I'm done. Cool. So why do we need multimodal machine learning? So the first, I'll give you multiple reasons, but the first more general, like overreaching reason is something related to what Professor Cho just said, which is like when we reason about the world, we use multiple senses, like we take into account what we see, what we hear, and what we read to jointly kind of understand what's going on around us and then make decisions. So if we want to use, if we want to build AI systems that can help us in like everyday tasks, or like, I feel like that's the end goal of all of this, to like make our lives easier and like, use AI to do the stuff that we really don't want to be doing. So if that's the end goal, then we really should be giving our models this ability too, of like, being able to take in all sorts of sources of information. Sure, that sounds like, very hand-wavy. So like, how about we talk about something more specific? So something I think which is really interesting and what kind of got me interested in this area was like, how do we teach our models common sense? So like, sure, a lot of this knowledge is already available in text, and over the course of this, this class, we probably learned that just by like training on large amounts of text, you can actually learn a lot of like world knowledge. And this has been proven like time and again with like BERT and like all of the successor models, which show that you can solve like sentiment analysis and question answering and summarization and so many other tasks just by like pre-training on large amounts of text. But then what about things which are not explicitly mentioned in text? So some things like you drop a ball and it falls on the ground, or if you tell a robot that it needs to like fold your clothes and put it in the closet, it needs to know that it needs to figure out where the closet is, then it needs to like hold it with the handle, pull it open, put the stuff in, close it. You know, this is not really explained in just plain text when you like put stuff in the closet might be there, but like how do you go through the stepwise process definitely isn't. So for things where you need physical common sense, like the ball dropping, or like if you leave a room and then that means you're no longer in the first room and you're in like some other space. So these are like very specific things which you can learn from other modalities. Then there's also like, there's a group like UW, which does a lot of like social common sense reasoning, which is another thing which is not so evident in just text. So you can like watch movies and kind of understand a lot of like, you know, social cues and things like that. So this is where the visual modality again helps you fill some of the lines. And then the third reason I think this is really interesting, like multimodal machine learning, is what I kind of want to pivot my research towards, starting like from what I'm working on now, which is like assistive technology. So these tasks are inherently multimodal because the people who like have problems using, you know, either online, understanding online content, or even like physical appliances, they need to like figure out when they read like some sort of device, what is like the allowed rating which you can plug it into, or like if your food has expired, or if a car like drives up to you, you want to find out if that's your Uber, for which you need to like be able to read the number plate. So all of these tasks are involve like vision and text, because you need to recognize the text in like the real world, and so like from text, from images, sorry. And I think this is like a really like impactful area of research, and that's why I'm interested in it. So I hope I've convinced you of its usefulness at this point, and I'll start talking about the actual science behind it. Okay, so what is multimodal machine learning? I'm going to describe this using tasks and data sets, because I think it's easier to like give you examples than just go on talking about it in there. So I'm gonna like just go over some common tasks, but oh yeah, I should mention that everything I talk about today will be in the space of image and text, but it's also applicable to like video and audio. And I think this is true more today, like in today's world, than it ever was before, just because all the subfields like computer vision, speech, NLP are all using the same kind of, you know, base architecture, which is transformers. And like if you're interested in this area, that's probably like, you know, the right place. And Professor Cho's NLP class is probably the right place to start as well, because it's the same kind of tools that you learn about here, which will be used across all modalities. If you're interested in like this general space, it's definitely like the main, you know, thing that you need in your toolbox. So make sure you like learn that properly. Cool. So yeah, the first one I'm going to talk about is called image captioning. So here, right now, in the first part where we're talking about the tasks, I just want you to think of the blue box as like some model, which, you know, we'll get into what that box has, but we're just going to talk about what goes into the model and what comes out of it, so that we get a sense of like what the tasks are. So yeah, so the first one is image captioning. This was one of the very early applications of multimodal, which became super popular. It's one of the early works I'll be talking about is actually one which Professor Cho was on during, I guess, his postdoc that he worked on. But yeah, so let's talk about the actual data so you get a sense of what it looks like. The one on the left is from this data set called MS COCO. You'll probably come across this, you know, several times if you get into vision or multimodal, because this is one of the most standard data sets. It was the first like large scale data set that was collected with human annotations, and it's pretty clean because they went through many, you know, rounds of filtering of the data. So yeah, so what it looks like is this image on the left, and you know, you have a caption, the man at bat ready to swing at the pitch while the umpire looks on, and you have about 130K images and 5 captions per image. So it's a very popular data set for image captioning. The one on the top right is called Localized Narratives. It's a very recent data set from Google. So it's slightly different and interesting in the sense that they actually ask the annotator to speak out the caption while they are collecting the data and while moving the mouse trace over the image, like the position in the image that they're actually describing. So you can see like if you have this color coordination, basically from purple to whatever red, you can see that the part of the text corresponding to that, it's like aligned in with the trace. So this gives you a lot more like fine-grained information. And if you want to learn about the alignment between image and text, this is like a really useful data set. And people have shown that tasks which don't actually depend on just captioning, like some others that I'll talk about later, like image retrieval, can also be helped if you have like the stronger amount of alignment. So yeah, there's a lot to be explored there. If you're interested, you should like look this paper up. And the third one that I want to point you to is like text caps. This is very hard because it requires OCR, which is optical character recognition, on the image. So you first need to like find the text in the image and then basically make a caption which includes that text. So it's like a step harder than either of the two that I mentioned first, and it's a pretty challenging data set. It's also pretty new. You can see it's from 2020. The second task I want to talk about is caption retrieval and image retrieval. So in the previous case, you just had one modality as input and you had the other as output. But during training, you have to basically learn how they go together, how they're aligned. But in this task, it's a bit more like explicit. I guess you have the image and text as input to the model, and you get a score. So this score is generally computed. You do some sort of like feature extraction, and I'll go into details about this. But basically, what happens is you figure out what's in the image, but you figure out what's in the text, and then you have to say how related they are to each other. So that's what this task is about, and it's actually like one of the most standard tasks that people report on when they like come up with a new model. So that's pretty important. The one on top, which is called Flickr 30K, is a pretty old data set at this point, I guess, yeah, 2014. And it's much smaller than Coco. I think it's 1/3 the size because it's like 30K images, but they still have 5 captions per image. So this is what I show here. But the task now is like, if you are given this image and a corpus of like, lots of sentences, which are captions for like random images in the data set, you have to find the most relevant one. And you would say like this problem sounds a bit ill-defined because, for a given image, there's many ways to kind of describe it. So why is this one text the most relevant? So that's what these people in like crisscrossed captions data set from earlier this year say. It was from a group in Google, and they basically said, we should be like having more dense annotation for this kind of data where you also have, they collected annotations between images. And so, okay, let me explain what this image is here. So small. Okay, I'll try reading it out because it's a bit blurry to me, so it might be a bit blurry to you. The first one says a flock of white sheep in a green field, and then the second one says a herd of sheep on an open field. So in the data set, these are both given as like ground truth positives for the first image. But you can see that the second image is also about sheep and also in a green field. So technically, your model should not be penalized if it predicts this as well. So that's why you have like annotations between images and between text, and that like gives you a better sense of like how your model is doing. Okay, the third one is referring expression comprehension and phrase grounding. So here it's a slightly different task because it's more fine-grained, if you like. In the previous one, you can see that as long as you have a general sense of what's happening in the whole image, you can probably like do a good job at retrieval, right? Because you're like, okay, there's a cat, there's a couch, and anything about a cat and a couch is probably high relevance. But what if you want to know like more in-depth or like more finer grained information? This task kind of checks your model's ability to do that. So as output of the model, you get a bounding box. So what do I mean by that? You can see that on the left, the top left, this there are two people, and apparently they're playing Wii. And so the task would be like, the girl playing Wii is the text which is given as input to your model, along with this image, and what you need to return is a bounding box around this girl. So in general, this task is hard because the text usually disambiguates multiple instances of the same class. So here both the objects or the main salient objects in the image are both humans, right? So you need to figure out which one's the woman in this. I mean, in 2021, I really feel like they shouldn't have data sets which do this, but anyway. So that's that task. And then you can also, instead of returning a box, return a whole mask around the image. And this is even more challenging because it has to be even more fine-grained. Like you can see the short deer here. There are two deers and it needs to really know what short means to be able to disambiguate this. And this data set is called phrase cut. It's pretty recent as well. And why it's interesting as compared to the previous data sets is because this was the first one where the entities in the data set are very long tailed. So like wipers on trains and like pedestrian crosswalk is actually very common, but like mark on chicken, like this is pretty specific. So yeah, it's interesting because it really like probes your model's understanding of these very finer grained or like long tailed concepts. Yeah, I put the like citations for these things. So like I'll send you the slides later if you're interested. You can like look up the data sets. Yeah, the next one, which I find really interesting, is called visual question answering. So here, given an image and some question, which should be text, anyway, you get an answer. So there's a bunch of like data sets in this space, but the first one that came out was the one on the top left. It's called visual question answering, and it's question answering really in the wild, because like look at this. This is like the poster picture for this data set with this girl having bananas in front of her face, and the question is, what is her mustache made of? And you really need to like understand what's going on in this image to be able to like answer that, I guess. What is a mustache, and then figure out like where it's on the face and all of that stuff. The problem with this data set is that, I mean, this was the first iteration of this kind of task. So, there's a lot of bias in the data set. People found that even by just looking at the question many times, you can find the answer without even looking at the image. So then, it becomes less interesting, and you can just use language priors, basically, like not for the one for the mustache, obviously, because it's adversarial, but like what is on the pizza, or like, is like, yeah, they are very like predictable answers most of the time, and that's why it's like less interesting than the one on the right, which was introduced later. It's called GQA. So here they take images from the visual genome dataset, which has very dense annotations, including scene graphs. So if you don't know what scene graphs are, it's like for each of the objects, you can consider each of the objects as nodes, and the relations are like how they're related to each other. So like cat sitting on a couch, sitting on is the relation between cat and couch. And they have like very in-depth annotation for this. So based on this, they automatically generate questions. So this is not, from humans. They know the ground truth and they know the questions. So like, or like the scene graph, so they can procedurally generate these questions, and they ensure, or like their contribution was basically saying that these questions have to be answerable just using the image. You shouldn't need like, random extra knowledge from outside, which is possible in VQA. Yeah, and the third one is Clever, which is a bit old now, but still used as a proof of concept, or like if you're building a new VQA model, you want to like try it out and iterate a few ideas quickly. This is what we did. That's what I'm saying. It's like much easier to do it on a small data set than GQA, which has 21 million question answers, because it's procedurally generated. So they can just make as many as they want, right? Whereas like, yeah, if you want to like quickly see how you're doing compared to the state of the art, it's easier to like do it on smaller, possibly like on Clever. And the last one I'm going to talk about is vision language navigation. This is something which was new to me also, and I learned about this summer, so I added it in. Here the task is like you are in an environment where the environment, your surroundings are given to you as a panorama of like 360-degree view of where you are, and that's your state representation. And then given some instruction, you need to follow the instruction to take the next action. So yeah, it's really interesting because it shows you like, this is like the cool AI that I thought about when I was starting out, like, yeah, you can just tell your robot where to go and it'll do the thing for you. So I guess this is like a pretty important building block in that. So it's an interesting task. And this is what it looks like. Let's look at the one on the far right first. It's the first data set that came out. It's called R2R, or room to room, because essentially that's what you need to do in this task, go from one room to another room, where you follow the instruction like the one below the gif. It's like leave the bedroom and enter the kitchen, walk forward. Okay, exit the bathroom, turn left, and exit the room using the door on the left with there. So you can see it's not very flowery language. It's like pretty straightforward. The instruction is just like you need to figure out the main like task to solve is like when you are given the image, you need to figure out like some important landmarks so that you know where you are, and then you can figure out like what to the right and to the left is. And I'll just say a bit about how usually they solve this task. They also have some amount of background knowledge at present the models, which is the navigation graph of the house. So you have prior knowledge that given a current state, there are some possible rooms that you can go to. It's not like, you just have to move in like anywhere and you can go bump into a wall. That's currently in the models, they don't try to solve that problem. They already know where you can go and you just have to pick one of the many options, which is pretty hard to solve. So yeah, and then the one on the left is a very recent one, which is taking it to another level, which uses Street View and like Google Street View and makes a data set out of that to do this in outdoor scenes. And yeah, here I guess you don't really have much of a navigation graph and your life is much harder to try and solve this problem. I haven't tried that yet. Just thought I'd put it because it's interesting. Okay. Any questions about these for now? Good. So now that we've seen a bunch of like tasks that are commonly reported on, I just wanted to also add a few like real world applications, because we kind of get obsessed with like benchmarks and data sets and how to prove that your model is better than everybody else's. But then the end goal is really not that. It's like how to make these models useful to like actual people. And this is the kind of data that you have in the real world, which is like kind of brings you back to the ground when you're like, oh yeah, my model is awesome, everything works in this very controlled setting of Coco or whatever. And then you see that the people who actually need to use these systems, like question answering systems, are the ones who can't really see clearly. So like, suppose they take a picture like this and ask you, what color is this pillow? It's quite hard to tell, right? The second one says, what denomination is this bill? You need like OCR capability to do this, but it's still possible. But a lot of these things have like images which are not centered, like which is not common in these standard data sets, have a lot of blur, and you really need more robust models to be able to like deal with things like this. And I also went to one of these workshops for these workshop tailored towards visually impaired people in one of the recent conferences this year. And they actually had somebody who was visually impaired take part in the conference and say like, it's cool that you guys have all of these nice models, but this is what we want. And apparently it was high precision. So like, they don't really care if you can find every tiny corner, like, thing in the image and like have some like high recall over like all the random stuff in your picture. If you can't for sure say that what's in the image is actually there, because they're going to take your word for it and like take this medicine or give it to their child or like, something quite important. And that's why they need it to be like very high precision. And that's, I guess, like an open challenge for these kind of models. So like, I showed you all the like nice and shiny data sets, but then this is like, where you should aim your life towards if you're like interested in this space. Yeah, so these some more examples. This is a slide from Peter Anderson's talk at the same workshop earlier this, yes.
For the previous slides,
yeah.
What is the golden act? Is that
Oh yeah. So okay. So I can tell you what that is. So this picture is taken from. I should have put a credit. Sorry, it's from the WizWiz, the same challenge that I was talking about. So how this data set came to be is because some grad student basically decided to make an app where he would blind people could basically take a picture and send the question along with the image, and then he himself answered the question. And he was interested to see like what kind of data this generates, right? And he saw that you kind of have like this high noise. Just fun fact, he actually made this app like open source, and like then it became like an actual product and companies bought it, and now he's not in charge of it. But before that happened, the data that he collected is now this challenge. The time there is the amount of time it takes for like an actual human to answer it. And they don't want it to take that long. They want it to be instantaneous, because the end goal is like, if you have images like this and you need questions about it as a visually impaired person, you want to like get instant feedback. So suppose I send like a really blurry picture. If I get a feedback that, can you take another picture that's a bit more centered towards the left, and like whatever, like some feedback which makes you get the answer quicker rather than waiting like 122 seconds every time I send like a picture. It would be much better situation. So that's the end goal. Yeah. So even in this space, there's a lot of like open challenges, which one is like describing rare visual concept, because let's think about like what kind of space these visually impaired people are going to like send pictures from. It's probably going to be from their houses or like some household scene. And really these data sets that we work on don't have that much long tail distribution over like food packaging or I don't know, some label on some medicine, right? Like it's just not something that's in their domain. So it's rare concepts that we need to be targeting and how to caption or answer questions on. Second is like understanding text, which I've already insisted on enough, I think. And the third is situated language. So Peter was like insisting on the fact that people don't live in just text or just in images. It's like the real world. So if you want your models to finally be like find the elevator or where are my keys, like these are still open challenges, and we need to put like all of these building blocks together to finally solve them. So yeah, so that brings us to like what's actually inside this blue box, and that's what I'm going to start talking about now. If you want me to stop or like go slower, I think I started speaking fast, so let me know.
Actually, that's a quick question. Yeah, are there like efforts to create more data sets that are like the ones that are kind of?
Yeah, so apparently they're all not public anymore. So these things do exist. I listened to a podcast. I don't know if you're familiar with these two folks at AI2 have this NLP highlights podcast. If you're interested, they speak about like really interesting things. Like they interview a whole host of like really interesting speakers, and one of them was about Wiswis, the researcher who works on this, and she said that it would be nice if there would be more data for people to like really work on, because this one challenge has I think 30,000 images and that's it, and that's pretty small compared to like modern standards of how much data we have. But the problem is I think like the industry kind of jumped on this idea, and for good reasons. I mean, it's a good thing that they're investing in it. And there are startups there's a startup called Seeing AI, which got acquired by Microsoft, I think. And yeah, so most of this work is now kind of in like industrial space, because they have the resources and they like kind of, yeah.
So like, no, finish your thought.
Yeah, that's how.
So like I've been using that for like a few years. It's called Be My Eyes. I'm
Okay.
not familiar with it.
Yeah, I've heard about it, but I don't know.
Yeah, so it's like it's where blind people can reach out to non-blind people.
Yeah.
And they basically perform a call. So it's a video conversation
Okay.
between visually impaired people and people with vision, and it's just helping them out about their daily life. So maybe like creating a similar app would help. But like I don't think first of all it's proprietary, so I guess it's I don't know if it's nothing. So it's definitely open source. But the similar app will definitely help, because I don't know if they record the data for the conversation.
Yeah.
And,
I guess like you have to take a lot of care also, because there could be the creators of this business, like the challenge I spoke about, they also spoke a lot about how hard it was to ensure there's no personally identifiable information, because these people like don't think before taking these pictures, and a lot of them had like SSNs in the picture, or like these really like things which you shouldn't be sharing, and so it's a lot of work and effort on the part of the people collecting to make sure that they clean this. And this is another reason why companies don't open source these data sets, because if it's internal, it's fine. Like as long as it's not being shown to the public world. A lot of these companies obviously have like PII information in their data. But yeah, that's another reason why it's like not really out there. Yeah.
Sorry, but can you repeat the questions next time?
Oh,
Like,
okay. Okay, so let's look inside this blue box I've been drawing. So the main like parts of any multimodal model, I would say, is like, I'm talking about image and text, but this would apply to like video or whatever else you're interested in. So in the case of image and text, so suppose we're looking at VQA here as an example, you would have like an image feature extractor. So what that would look like can be like a CNN as, a ResNet, VTG, whatever your favorite deep CNN. And then for the question, you need a text feature extractor. Before transformers, this used to be like some sort of Rcnn like LCM or GRU, which would like have a, you take the final state of it as the representation of the text. And then multimodal fusion, basically what it means is like you need some way of kind of aligning these two, right? You need to know which parts of them are relevant to the other. So there's many ways of doing this, and we'll discuss through the different models that I show you how this works. But you can either do it very early on, where you actually let the text feature extractor actually have access to the image feature extractors embeddings, or like the other way around. Or you can do it in the end, where you have the two feature extractors do their thing separately, and then in the end you have like some sort of attention or dot product or whatever, which gives you like the multimodal fusion. And then finally you have a classification head, which usually is like just a MLP or like even a linear head on top of the final embedding that you get to give you an answer. In the case of like long form question answering, you would also have like a language modeling head, which actually generates the answer just how you would have it in a normal language. Just now it's like conditioned on the multimodal embedding. So let's talk about some early influential approaches. The first one, I should mention that I tried to like put these boxes here, which are color coordinated with this one. So that like, the green one is the image feature extractor, the pink one is the text feature extractor, and yellow is this and blah. So like how they change across the different models without like having to look for it too much. Yeah, so the first one I want to talk about is Show, Attend, and Tell, which is the paper which Aishwarya worked on. And the main idea here is that you use an Rcnn with attention to the visual features. So the visual features in this model, as I've written here, is just a normal CNN. And yeah, so the way they fuse the two modalities basically like by letting the Rcnn look at the image features. So I would say it's like pretty early fusion, because just generating already, you're like for each time step, you're looking at the image features. So this is what it looks like. You have an input image, you take a convolutional feature extractor, so you get some feature maps for this image. And then the LSTM for each time step when it predicts a word, so it starts with beginning of sequence, and then you condition on the or you like attend to the image features and you predict the next word, and so forth till you like predict end of sequence. So this was like kind of game changing, because you could see that your model actually looks at relevant parts of the image. You can see here for a little girl sitting on a bed with a teddy bear, you have the attention of so what we see here is the attention map, which shows like which part of the image is attending to. You can see that when it says girl, it's actually like high on the right area, so that it gives you a sense of like interpretability, this sort of model. So like everybody was pretty excited about this, that it works so well, and like you also get some interpretability for free, that it's looking at the right thing. Okay. This paper, it was called Bottom-Up and Top-Down Attention for Image Captioning and VQA. It was a pretty influential and seminal paper, so you should definitely look this up if you're interested in this area, because it's till date, even with all of the transformer approaches and everything, this is the paper that everybody goes back to get the image features. Like Peter Anderson, again, the same person from BLN, he basically trained some visual features. I'll explain how. But he made a Docker image or something at that point in 2017, and people till this day still like just use that pre-extracted image and don't do it themselves. So yeah, it's pretty important, this paper, and it's like so I should say it. So the main idea is, instead of how we had the attention over the entire grid features of the image previously, now we have attention over objects in the image. So how do we get these objects? Around this time or just before this, there was like a bunch of object detection papers, like the area of object detection really matured. You might have heard of faster Rcnn, which is the kind of standard object detection architecture, which is used even today. And so in this paper, they combine the faster Rcnn approach to extract image features, which is why I have this CNN-based object detector here, with the ideas which were previously existing, like from Schwitt and Intel, where you have an Rnn to generate the actual caption. So what it looks like, or like the main idea behind this paper is like the one on the left is if you were just attending over grid features over the whole image, that's what it would look like, right? The unit of information in the image would basically, it's zoomed out because it would be the pixel level, but this is the general idea. But the thing on the right is what you would get if you were doing it like region-based or like object-based. And this is like quite important because you save on a lot of compute by just like not looking at everything and just having some sort of like really salient object detection. So let's see how this like actually affects the prediction. The one on top is something like Schwitt and Intel, where you have attention over the whole image. So you can see that the attention map is shown with the image behind, basically for each of the words. And the sentence predicted for this image as a caption was a man sitting on a toilet in the bathroom. That sounds reasonable. If you didn't look at the image, you'd be like, yeah, maybe. Like if it's about a bathroom, he's probably sitting on the toilet. But if you look at the image, you'll see that it's actually a couch that he's sitting on. This is something very commonly that happens in image captioning models, where they use like language priors to just say the most reasonable thing that would happen in text across the whole corpus. But you don't want it to do that. You want it to actually look at the image, right? That's the whole point of the task. So if you do this object-based kind of approach, which is what they show at the bottom or up down, you can see that because you've conditioned on this actual object couch here in the bottom block here, it actually predicts couch, a man sitting on a couch in the bathroom. So I think this is like pretty interesting, and like it relieves your multimodal part of the model a lot of the I think like actually figuring out what to say in the caption and figuring out what's in the image and like how it aligns to the text is a lot to do. Whereas if you actually just give it the relevant parts of the image that you want it to talk about, it's like cleaner, at least as I see it, like more elegant. Okay, so let's talk about very quickly about faster Rcnn because it's very important. So you have an image which goes through a CNN and you get some feature maps just like before. But the key idea is that it's what you call a two-stage detector. I'm not going to go into much detail, but you should know what this means. So in a two-stage detector, there's two parts of the model, one which actually just proposes parts of the image to be objects. So it just says, this is probably an object, this is probably an object for different parts of the image. And then the second part, which is the classifier, will say what object actually is and what the bounding box of it should be. So that's the general idea. But more specifically, once you have the feature maps from the conv layer, what you also get, or like what is part of this approach, is to have a set of anchors. So anchors are essentially a set of proposals, like or potential boxes, which are of different shapes and sizes and aspect ratios. So they can be like longer than they are wide, because some objects will be, suppose it's like a stick, it's going to be longer than it is wide, or like if it's a couch, it's like wider than it is long, things like that. So they have like a predefined set of like these anchors which are part of this model. And what the region proposal network does is that for each of these anchors, for each of the points in the image, it says how likely is this to be an object. And then for each of those things, you take like the most highly ranked proposal boxes, take the feature representation for that anchor box, like inside that proposal region, and then classify it using like the last few layers of the CNN in the second part, which is shown on the top, which is called ROI pooling. So that's the general idea. And so what Peter Anderson and the other collaborators on this paper did was train this network on this data set called visual genome. Prior to this, mostly people were like mostly training on COCO, which has just 80 classes. So why this is important, I will insist on it like again later, but I just want you to like appreciate the fact that your object detector is the main source of information from the visual world for your model, right? So if your object detector can find a cat, yes, you can reason about it later in the model if the question is there a cat in the image? But if your object detector didn't know what a cat was in the first place, it's really hard for you to answer this question, right? So what they did to like sort of get past this problem of fixed classes on COCO is train on visual genome, which has 1600 object classes. So it like expands your vocabulary a lot, tells you about a lot of like, long tail concepts. And in addition, this was the first time that he also, like this paper basically also trained a attribute head. So for this bench, for example, it also predicts things like it's just a softmax over a bunch of attribute classes, as well as like no attribute, because maybe you don't know the attribute for this, it doesn't have a product. But for bench, it would be like worn, weathered, wooden, gray, etc. And this really teaches your model a lot more than the, just grid features we're giving you before this. And that's why it's become super popular as the go-to feature extractor for the image space for multimodal models. And on the right, you can see what the output of such a system looks like. The West is probably one of the classes in visual genome, which is why you have a box around it, and it has the attribute blue, so your model is able to predict things like that. Any questions about this?
Yeah, for the different attributes, is it basically like, you might not, but like, is it just like basically if it's above a certain threshold with the softmax that gets assigned, or there like a certain number of attributes the model aims to assign?
Yeah. So I think it's trained with just like a binary cross entropy. So like you said, basically you just predict over a set of classes. Many of them can be true. So it's a multi-label classification, and then you just take the ones which are above a threshold and say these are all positive. Okay, so now there's one paper which I want to talk about, which also uses a more like symbolic kind of approach. It's called inferring and executing programs for visual reasoning. So all the papers all the models we looked at till now, basically just do everything kind of with a neural network, which is just like looking at the image, attention, and then you predict. But this paper takes a slightly different approach. What they do is like actually predict the program that needs to be executed to get the answer. So it's like more neurosymbolic than just using neural networks the whole way. But how does this look? So suppose they want to solve a question on Clever, and the question is, are there more cubes than yellow things? And this is a very typical of a kind of question in Clever. It's not very interesting visually, but there's usually many hops of reasoning, or like you need to compare many things in the image to be able to answer. So there's a sequence to sequence model, which is LSTM, the LSTM based model you can see, which is called the program generator. So that will generate this prefix notation program that you've seen, or that you can see here, like filter, shape, count, etc. blah. So it has like a predefined vocabulary of these program words. And what it generates is like basically this program that if you execute on the execution engine, then you would get the right answer, or like that, then that would produce an answer. So how they train this is kind of 2 steps. In the first step, they train a sequence to sequence model, which has ground truth annotations for these programs. So you make sure your like seq to seq model is pretty good. And then after that, once it predicts like some program, you actually use something called a neural module network. This might be a new term to some of you. What it is like it's a pretty interesting paper from Jacob Andreas, who is I guess now a professor at MIT.
Yes.
And yeah, so he proposed this approach where you have these building blocks like filter, color, yellow, count, which themselves are neural networks. Okay. And the way they are organized or put together to form a whole architecture is decided by this program. So it's in the end, like, the execution engine is still a CNN, which is like organized in some particular way. The weights are like for each block are decided by like, what type of unit it is. But it's essentially like a CNN whose ordering is, or like how it's put together is decided by the program. So if you're interested in that, you should look up neural module networks. It's a pretty interesting paper. But that's the idea they use here, and they get pretty good results. And this was a pretty, a interesting and important paper. And for the clever space, we should look at this. Yeah, I think this is the last one in the early influential approaches. This is something called neural baby talk. It's from this really cool researchers called Devi Parekh and Dhruv Bhatia from Georgia Tech. They're also at Facebook, I guess. And yeah, so their group is really nice for multimodal papers. So if you're interested in this space, I would look them up. But yeah, so what this paper does is it is an image captioning model, and the main idea is you generate a sentence template where you don't know what's going to be in the positions for the objects yet. You just know that it's something you can attend to the image to get the object, and you fill in these slots in the second step using just basically using attention. So what I think it'll be clearer if I show you the diagram and compare to what we've been seeing till now. So the one on the bottom is the typical architecture we've been looking at. You have a CNN, con features, Rcnn, which attends just to the objects in bottom up, top down, and then gives you the caption. So what they do here is like this two-stage approach, where in the first stage, they basically just predict it's going to be a visual word, and which one of these it's going to be. It doesn't like actually put the textual word for it yet. And then in the second stage, the object detector tells you for this region, the label or the class predicted is dog, or like whatever, puppy. And so they like plug that in here. So that's the general idea, and it works really, really well for the caption.
Why is it called neural baby talk?
No idea. They had a paper before that called Baby Talk, which was not neural.
Oh, okay. But then why was that called baby talk?
I think they meant like that. I don't know. There's some reasoning in the original paper. I don't remember, but I think it was like, yeah, that's how babies learn to talk or something.
Okay.
Yeah. Okay. So now I'll talk about transformers for vision and text understanding. This is like the main approach that everybody uses now for this space. So this is the transformer architecture. I guess you already know what this is. I'll just say that you have some inputs, you get some positional embeddings, because without that, then like the transformers permutation invariance. So you need some information about sequence ordering, and then you have your multi-head attention and feed forward. So this is the encoder on the left, and on the right you have a typical transformer decoder, which first has like multi-head attention on its inputs, and then also has a cross-attention layer to look at the last layer of the encoder. And then you have another feed-forward layer. So this should be pretty familiar by now, because I'm going to assume you know what this is, so that we can talk about how to use it for multimodal. Cool. So here in this approach, you have everything, all the keys, queries, and values are all coming from one modality. So till now you've been looking at it just for text. So, but now we're talking about having images and text as inputs. So like, how do you deal with that is what I'm talking about now. So basically, there's 3 different main types of like attention mechanisms that you can use, and each has its like advantages and disadvantages, which we'll talk about. But the first one is called co-attention. So what this means is like, suppose this, so HR basically stands for hidden representation from regions. So just assume they're like image features. and HW is like hidden representations from words, so they are image features. So basically, if you have queries coming from the region and you attend to the language part for the key and value and vice versa, so you're kind of like going cross for both directions. This is called co-attention, and you'll notice here that the models themselves are separate, right? So like the feed forward layers and stuff will be separate, just the multi-head attention will be like going across. So this is one way of doing it, and we'll look at a couple of models that use this approach. The second one is called merged attention. So here, the diagram is a bit confusing, but just think of it as your query will be attending to everything. So like there's no discrimination between like if it's coming from text or image space. So like self-attention, each point in your input looks at every other point, right? So like in the earlier case, each query was looking at only the keys and values basically from the other modality, but here it's like there's no like discrimination between the modality. It's just like one long sequence. That's how you can think about it. You concatenate it before you like pass it into the model, right? So, and the third one is called modality specific attention. Here you can see that there's very little crosstalk between the two different modalities. It's like, the vision part is doing its own thing, the language is doing its own thing, and then you'll have like some way to put this together in the end. So this is, I would say, like, the most, probably the least performance, like best performance giving model, just because like there's the least amount of crosstalk, whereas here you have the most amount of like information flow between the two modalities, and this one is somewhere in between. So let's look at examples for each one of these three. The first one is Lexmord or Wilbert. So I'm going to be showing you the architecture for Lexmord, but Wilbert is pretty much the same. These were like, the first one is from UNC Chapel, like Mohit Bansal's group. There's also very good for multimodal, and also worth looking at that group's work for work in this space. And Wilbert is again from Georgia Tech. Cool. So what they do is, let's look at it in a little detail. So suppose you have an image and an object detector. So like the faster Rcnn approach that we were talking about earlier. It extracts some region features for each of the detected objects, right? So that's what we call ROI features. And positional features are the bounding box information for each of these boxes. So that the actual height, width, and the XY coordinates of like one of the coordinates. For the text, you would use like word embedding. So generally they just use like word initialization for the word embedding. So it's just like regular language model that you train on just text. And then what you do is like have these two streams. So this compared to like this approach should look familiar now, because like you have two separate kind of towers. They're called like two tower models because of this, where you have separate feature extractors, and then you have some layer of cross modality interaction. So you have like just object features, just text features, and then that model diagram that or like the schema that I showed you for co-attention. This is what I was talking about. So at the output of this part, they take the visual output there, and language output, and how they actually train this, or like how it's pre-trained is what I'll describe on the next slide. So for most of these multimodal models, there's a bunch of what you call pre-training or pre-text tasks, where you're trying to like make sure that the visual modality and the text modality, like they're kind of learning to be aligned, or how they're like correspond to each other. Okay, so the first one is called Roi Feature Regression. So what that means is like, you can see here at the input of this object relation encoder, some of them are blacked out. So basically they're just like zeroing out these features, and at the output you need to predict those features. So similar to how you would do like mass language modeling in Word, this is just like the equivalent in image space. Detector label classification is just like for this given, each of the region features, what is the class label? It's pretty straightforward to like implement that. And the third one, which is quite important, and people have shown it that it's probably the most important one, is called like cross-modality matching. So it's like in a batch, you have a bunch of images and a bunch of text, and for each of the so if you make a batch of like for each text, all the other images are negatives for that, so you can construct like a batch of inputs for this task such that from a training example, the true positive is like the image and the text, and every other image is like a negative for that text, and vice versa. And you teach a model to like basically distinguish between matching and unmatching, like not matching examples. And then the last one is like basically just the normal BERT mass language modeling objective. It's just that they call it mass cross modality matching just because they're in this model you have access to the image. So if you block out this word like for rabbit, who is eating? Okay, so for carrot, I guess, suppose you like mask the word for carrot, like they have here. You can still look at the image to like know what the word is. So that's the reason it's called mass cross modality language modeling. So these are like very standard retraining tasks which are used by many models. So it's worth reading this paper. It was one of the first to like do this.
Sorry, I have a question, just the like little yellow box that is, I guess like kind of what's that function again? You like already kind of talked about it, but like.
Sure. So you might have seen like, if you've seen the BERT paper, they add like an additional embedding right at the beginning called the CLS token. So that token is generally used as like some sort of like compressed representation of the rest of the sequence, and is used for like classification. I guess that's how it gets its name.
Yeah.
So the same way they also add like this extra token. So it's there right from the beginning here and here. And so that's why they like it can have any function that you choose it to have, basically. So here they're using it as the embedding which tells you, which is used to like do the prediction whether it's matched or not. Yeah, but it's just that that token is like never masked out during your mass language modeling, so it has like full context for the entire sentence, and so it's used for like cross modality. Yeah. So the second one is like I just chose a couple which show you each type of attention. So the second one is the merged attention. So the feature extractor is the same CNN. It doesn't use, so in the previous ones, right? In the previous one, I had transformer as the text feature extractor, and transformer also as the multimodal fusion, because basically that's what you have. Transformer both of these, and then in the text, and then the multimodal fusion. But now basically you don't have a separate text encoder and a image encoder like explicitly. It's just one big transformer where you feed everything as a sequence. So you first feed in, so you still have the object detector, which takes in the class information and the bounding box information just like previously. And then I should mention that I think it's like implicitly stated here, but I should say it clearly. For each image, they extract a fixed set of boxes. So it's in all of these papers, it's usually 36. Some number that someone chose and everybody stuck by it. But yeah, so this is like suboptimal because you might not need 36 to describe an image, and sometimes you might need more. So like it's kind of silly to like just set that number. But yeah, so the 36 features are basically what are passed in here as region features. And the text over here is basically the caption that comes along with it. And this kind of model, like Uniter, Lex, Mert, Wilbur, they're all trained on image caption datasets, such as conceptual captions, Coco, Flickr, whatever, like all of these datasets which have aligned image and text pairs. And yeah, so the objectives for training this model are pretty similar to the one I described before. It's mass language modeling, region modeling, and like this thing that they introduced is called word region alignment. I won't go into much detail, but at a high level, it's a way to make the distribution over the images and the text similar using some optimal transport technique. But yeah, essentially what it does is like try to make sure that if a region and text are similar, then they're like marked as like this is relevant or whatever. Okay. So I hope you see the difference between Uniter and the one before. There's this one transformer here taking in everything versus two separate towers. So I have a question for you. So the question is, I described like what masked region modeling does. Basically, it has a sequence of regions, and you mask some of them out, and then you basically have to predict what the value of that is by regressing it. So recent kind of probing papers which actually check which of these tasks are really useful for good multimodal understanding have found that this one is quite not useful in retrospect, and like I guess I want you to think about why that is, and if you have any guesses for why it would not make sense to have this task for training.
You're saying specifically the MRM?
Yeah, specifically. Yeah.
Just because it can more easily learn that from that language model, and it just kind of relies on.
Well, not from the language model, but you're close. So like think about why it would like not work to just mask out a few regions.
Is it because of the way?
Because the caption already has this.
No, you wanted to learn it from the caption. That's the point of this task. But like I'm just saying, letting the model predict some region features, which are the output of, there's a CNN, and then the faster Rcnn pipeline I showed you, the output of that is what you have now, and you're trying to like mask some of them. And also keep in mind that it's always 36 and you're masking some of them.
Is it because of the way the patches are defined? I mean, they might not be related to each other.
So yes, it's because of how they're defined, but it's especially because they might be related to each other. So it's because you're masking some and trying to predict the others. So when you have like 36 region features, many of them are oversampled, so they could be overlapping. And you're basically like not making your model do anything hard. So it's a like kind of trivial task for it to learn. And that's the obvious answer. And then there's like a more subtle one, which is the fact that this region feature is the output of a multi-scale CNN, which has already, seen the image at many different resolutions. So the features at the end are like extremely correlated across the whole image. So just because you're masking some like final region features out doesn't mean the others don't have like information about this. So it's like pretty easy for this to like bypass it somehow. So what people have been trying to do in the vision community is something that I wanted to show you. And a cool thing would be to combine the two. I don't think anybody has done that yet. So the idea here is, I don't know if you've seen OpenAI's DAL-E model. It's a very cool, text to image synthesis model, which was all over the news because you could have couches which look like avocados or something like that. But the idea that was proposed in this model was to learn a visual code book. So what that means is like, suppose you have an image, you learn a discrete VAE. So if you've heard about VAE, what VAEs do basically is like, you encode some image, not to a point, but to like some sort of like a region of space, and then you decode from that to reconstruct the image. That's how you train it. And when you train it like that, during inference, you can sample from this like Z space or like latent space to get a variety of like outputs. So high level, maybe not the clearest explanation, but in this case, the latent variable is basically discrete. So what that means is like, if you think about it like without math, what you want to do is like go from an image from some part of the image. So suppose you divide the image into these patches, right? For this top left part, you want to predict one of 5,000 suppose visual tokens. These are just embeddings, and they are trained end to end, so they will be trained as part of your model. But you will say that this patch in embedding space is the closest to this one token, and that's how you choose this like number. And during training, it's trained to like decode back this original image, and that's how the actual embeddings for these different visual tokens get trained. But for what you need to know is that for this kind of approach, each patch in this image has two separate like views, you can say. One is like this actual pixel representation of that patch, and the other is like this visual token that it corresponds to. So what they do in this approach, this is like a really cool paper by Microsoft, is they apply the same idea that we use in like NLP to image patches. So here the input is actually just the patch. It's not like, you know, the output of some multi-scale CNN which already has correlated features. So this task now gets much harder because, you know, there's no overlapping, there's no like, information sharing. Basically, you just have patches of the image and you like make it a sequence by having position embedding. And at the output, you predict the corresponding visual token. So this would be like a much harder pre-training task than, you know, mass region modeling, and it's just something that I thought would be interesting for you to know about. If you have questions.
So in the previous slide, does it matter the sequence of the visual features? Does it matter if the sequence is different, like how they're fed in?
Yeah, no. So that's a good question. It's in this case, like the sequence positional features make most no sense for the region features, like you said, because they're just like a set of features. So there's another paper which looks similar to this. It's called Vivo. But yeah, essentially the idea is like they do a similar kind of training, but instead of actually like having so Uniter does this word region alignment for this particular reason because there's no real like ordering between the regions. So you don't know which one of the regions are mapped to which one of the text, right? Like, you know, when you want to do inference. So what Vivo does is a slightly different approach. They use a matching, like a Hungarian matching algorithm. So it's basically a bipartite matching between the tags. So like suppose words in it's not a sentence, suppose you just have like region features and their labels, and you need to learn a mapping between which ones are true. And so you can use like other approaches other than optimal transport, but you're right, the region feature shouldn't have any like ordering information. Here they just like don't use any like positional information. You can see that for the text embedding, there's token and position, but here it's like Rcnn and location. So location is just the bounding box. It's not actual like position in the center. Okay. This is another of the same kind like Uniter, another merged attention. And I'm bringing this up after Uniter just because it solves some of the problems of like the overlapping boxes and the fact that there are 36 and that they may be oversampled. What they do is like in addition to having just the region features, they actually also give the labels of each of these region features as input. And that's basically the main difference. And they call it like object tags. And just by adding this additional thing as an input, it like alleviates a lot of the multimodal fusion work from the transformer because it kind of uses this as a pivot between the first and the third thing. So yeah, they got really good performance just by making this like one pretty small change. And they were pretty much the state of the art on a lot of the benchmarks for quite a while. So it's a pretty important paper for you to know about. Okay, this last one in this series is like the type 3, which is, you might have heard about Clip, also made a lot of headlines, I guess. Yeah, so what the idea of this is like you massively pre-train on, you know, a large amount of text. A line is like 1.9 billion image text pairs. It's from Google. They have that much data. And Clip is, on the other hand, I guess 400 million image text pairs. And what it looks like is you have a text encoder. So in Clip, they try like a transformer as well as I think it's just transformer. And for the image encoder, they use a CNN. They also try with the transformer, but let's assume it's just like image features that are pooled. So like some 2048 dimensional representation that is common to like extract from a Rcnn, for example. So how you train it is you take some text, you make a batch out of like, this is what I meant by making a batch of positives and negatives. So suppose you have Pepper, the Aussie pup. This is the first one, this is P1. And you have this first image of this. apparently pepper. This is the image representation for it. So what this matrix basically tells you is that for this image, all the other texts are negatives, and for this text, all the other images are negatives, right? So it's by default, by construction, basically. You just like make sure that the model understands that for this image, the representations for the text that are not the one that it's aligned to should be further away than the one where it is. So the I1.T1 here is a normalized dot product. So it's a cosine similarity between these two representations. And basically, you try to make the diagonal as close to 1 as possible and the rest as close to 0. That makes sense. And then once you have this model trained, they show that you can do basically like zero-shot transfer to other data sets. Basically, you just encode the image using the same CNN that you had trained here and feed like a templated version of all the classes that you have trained your model for. So suppose a photo of, and then you put like plane or car or dog or whatever. And then you just take the one which has the highest score. It's like pretty straightforward. And it's basically casting classification as like a text retrieval problem, right? Like we've already seen this kind of model, like where you can feed the image, feed the text, and choose the one with the highest score. So that was like an important takeaway from this, that if you use language, instead of using fixed classes, you can like get for free, you can get like zero-shot transfer to a lot of other data sets. And I guess a nice visual that you can take home from this paper is like they showed that if the blue curve is training this model as basically like an image captioning model. So if you have an image representation and you need to like generate the sentence about it, that's what it would look like using a transformer language model. This is how it would do. If you were instead just predicting a bag of words representation, so you don't really care about the ordering, but you just want to predict like some pool representation of the sentence, you get slightly faster, more efficient model. But the best one that they have, which is the one which we looked at here, is the contrastive approach. This is a very like common technique used in many other fields as well. Like if you probably come across it of info NCE, or like many other contrastive learning like algorithms. So yeah, so they all basically have the same idea of like in batch positives versus negatives, and they show that it's like basically 12 times more efficient to do this contrastive learning than to use like a language model. So yeah, any questions? Let's talk a bit about like trade-offs. So at this point, is it clear what a dual and a cross encoder is? I might not have mentioned. So what's a dual encoder? Anyone? For multimodal.
That's just kind of two towers that you're talking about.
Yeah, exactly. And cross encoder is the one where you just have one transformer and you feed everything together. Okay, so I guess the question now is like, which one do you think is faster for doing the same? Okay, let's take a task. We're talking about only image text retrieval, right? So you have to encode images and text and be able to find the text that is most relevant to a given image. So which one would be faster between the dual and cross encoder, and why? Yes, and so what advantage do you get by using the dual encoder because they're independent?
Can parallelize them?
Yeah, so another way of saying it is like you can basically compute the representation for all the text and all the image, cache them, and basically when you need to do inference, you just like already have them ready. Whereas if it was a cross encoder, basically for every pair that you want to check, you have to feed it in. So you can't like at once just make sure you have all the text, all the image, and then check. When you want to check for the next text, what is the most relevant image, you have to feed that text and every image in the corpus, and then get the score for it, which is like really suboptimal or like inefficient. So speed-wise, it's much better to do dual encoders. What about performance? What do you think? Like this, obviously you can't tell me, but what do you think?
Cross encoder is probably better.
Yeah, because there's like way more like attention between the two modalities. So this has been like proved multiple times, and there was a paper which actually did a very controlled study on this and showed that much smaller models can be used if they're cross encoders than dual encoders on the same amount of data, because they're just way more efficient at using this data.
For the you showed us the dual, like fully separate, like the third one and the first one was kind of like they had some.
Yeah.
Cross, do you still get some benefits from parallelization with that first one?
No, because you still, the later layers still require you to have all of that.
Okay.
So what I'm comparing now is 3 and 2 basically, which are like the main two, like the first early approaches for multimodal, like the in transformer space, like Flexmod, Wilbert, they were all 1, but people basically just moved away from it and mostly all do like 2 or 3 now. Okay, and the third factor to kind of consider is noise sensitivity, and what I mean by this is like the data sets that we typically use for training these models. You can either say, I'm going to stick to the lower data regime where low is still 3 million, by the way, where you use like conceptual captions 3 million, which is still web scrape, but it was heavily filtered, or use Coco, which has 500,000, very clean. You don't have like noise in the form of like your image not even being about the text, which is very common in bigger data sets. Or you can go to the other extreme, which is the kind of approach Google papers recently have been taking, where they just train on like 1.8 billion, like Mural I think was like 6 billion. So yeah, just like a scale that is on the other extreme. But what you get in those data sets is a lot of noise. Like I've personally looked at some of this data because like I interned there, and like it was crazy. Like some of them are just like screenshot 101, .jpg, and then there'll be the image. And that's actually data which is in this corpus. So like you don't learn that much from those kinds of things. And so one option is to filter down that extremely noisy data, or just say that, yeah, my model can learn it. So now, which one of the two do you think would be like more sensitive to this kind of box, I guess? This is not obvious, and I don't think I have a reasonable explanation for it, so I'll just tell you. So the dual encoders are like way less sensitive to this noise, as opposed to the cross encoders. This was also shown in that control study I was talking about. So they show that like when you're using cross encoder models, you're better off training on smaller amounts of data which are cleaner, and you'll get like much better performance than if you train on like large amount of data, because it's like it learns like very bad parameters there. Cool. So just one paper to show you that it doesn't have to be like black or white. You can be smart about it and like kind of find a trade-off between the two approaches, between dual and cross encoder. This is a paper from TU Darmstadt. So it's like you have on the left a cross encoder model where you pass everything as one sequence. The second one is what they call M, and I call dual encoder. Is like you have these two separate things and you make a sign. So what they do is like very straightforward. They first take your corpus of image and text. They first have this dual encoder model, which gives you a set of, for a given image, a set of text which are high cosine similarity, suppose, right? So you decide what your set size of your set is. So suppose you take like 50, the top 50, and then for those 50, you then feed them to a cross encoder. So this is like, you retrieve really quickly, and then you re-rank the retrieved set of image and text to get like a better, cleaner prediction in the end. So you like trade off on like performance in the beginning, but I think these are like tricks that people use in like information retrieval a lot, like, have a quick beginning model and a much more intense and finer grained second model to like filter through the noise, like filter through noise and then like get the best results. And they show that if you share the same weights, like share the weights between these two models. So here you can see there's a transformer, and like a separate one here. That's why they're different colors. But yeah, so the last model is all of them are the same. It's just that you just like reuse the same model twice to get, for the you don't feed in the image, you just feed in the text, and this is that part. Whereas on the other side, you feed in the image but not the text. But the parameters are shared between all three of these, and they get the best results by doing this. So yeah, this paper is called retrieve fast and re-rank smart. And then there's another one called thinking fast and slow. So yeah, there's very similar papers came out at the same time. So yeah, it's worth looking at that. And then finally, I've been talking about like multimodal stuff and how it's useful. There's also the fact that there's, you might learn stuff from multimodal context that might help with unimodal tasks. So you've probably seen a lot of this superglue related tasks in this course. This paper actually was pretty much the first one that trained in a multimodal context and showed gains on superglue. So yeah, so how do they do that? Their point is like, if you have a question like, their goal was still to like do well on multimodal tasks, but by using additional unimodal data. So it's like, who's standing behind the baseball player? Coacher, it's not my typo. Coacher, umpire, and spectator. So like, if you have additional context like the one on the right from Wikipedia, they claim that you can have a better answer to this kind of question. And what it looks like is, suppose you have this one image paired with the text in the middle. They retrieve, using some retrieval model, a bunch of more images which are also relevant to this image, and a bunch of text which is also relevant to this text. And on the other side, you have like these positive and negative pairs. They actually take a lot of trouble to like make good hard negatives by editing at a word or a phrase or a sentence level. So what I mean by that is like, the baseball player readies to swing at the pitch while the umpire behind him looks on. That was the original thing. So basically, swing at the pitch, they basically change at the phrase level to have in the room. So this is like a hard negative that your model needs to be able to like, tell the difference between. And they have many examples like this. But the one on the left is probably like a much easier negative, rides a horse in the court, like it's some random thing, which is not really related to your model in that way. So they've shown both, because the ones on the left are usually the ones which other models use as negatives. Whereas if you like learn from hard negatives, you are better at discriminating. There's also a data set called Bison, where you can have two images which are very similar. I forgot to put it on the slide, sorry. It's like there's a plate with carrots on it and on a red tablecloth, and the other image will have like asparagus on it or something. But like the setting will be pretty much the same. And you need to say which one is the correct one if I say carrots. And this like very fine-grained image understanding is pretty hard even right now for our models. Yeah. So this is still the merged attention approach where you have one transformer which takes all. When they have only one modality or the other, they basically just don't give the other as input. And that's the only change. Yeah, so we're gonna stop here with some water and let you take that in. I didn't realize this was so tiring.
Yeah, welcome to my house.
Okay. This part now I'm just gonna talk about or like motivate the reason why I worked on the paper that I did work on. So the drawbacks of what I call the detect and learn alignment approach, which is all the approaches we've seen till now, right? They all like do the detection, and then once you have like these frozen image region features, those are not trained anymore. Like the gradients are not back propagated into this. Why I'll get to, but basically because they're okay, I guess I'll get to it right now. It's because the feature detector or the feature extractor, the faster Rcnn, is not end-to-end differentiable. What that means is like these features are not going to be fine-tuned for the downstream task. They're just like extracted, frozen, and then you use whatever you have. So like the problem I mentioned earlier, like if there's no cat in that 36 regions, you can't do anything about it. Basically, you're like not going to be able to answer questions or like do whatever caption or whatever else. The second is that the features are oversampled. So suppose you want to answer like how many kind of questions, you're going to be like in trouble if the same box or region feature is like there multiple times, and if you're trying to answer question like counting questions. And this has actually been shown to be like I think there's proof that this is a problem because the paper which has state of the art in counting kind of problems doesn't use object detectors, like doesn't use this approach. They actually attend to the whole image, and they have like a separate module that specifically like is designed for this. It's a paper from Facebook. So yeah, so that's a problem. And then the third one is that it depends on whatever label set that your detector was trained on. So if it's COCO, it's 80. If it's visual genome, it's 1600, but still bounded. Like if you see a new kind of category or a new combination of a category and attribute, right? Something you haven't ever seen before in training, your model can't handle it anymore. So that's these are the main drawbacks. Yeah, so the point I'm making here is that the performance for all of these models till now was bottlenecked by the object detector. So that's the main problem that I worked on. Another like image just to show you in terms of numbers. COCO, as I said, was 80 classes. VG was 1600, and then there was a paper recently called Retrieval, where they basically combined a lot of object detection data sets. So they ended up with like 2.49 million images and more than 5 or 5.6 million image text pairs, but still only had like 1848 classes. So like, I guess that's a pretty good coverage, right? You know, for most cases, that's probably enough. But the question was like, can we do better, but without going in the same like kind of just get more detection data set kind of approach. So this is the paper that I worked on earlier this year, where there's a bunch of people from FAIR and Jan, who doesn't need any introduction, and Nicola, who is a postdoc with Jan. So what is modulated detection? The idea behind our approach was this concept of modulated detection. And it solves this issue that I just mentioned, that if you have this weird new object that you see in the wild, which is like a pink elephant, no, there's not something that you see usually in training data. It's actually something I made in Photoshop, so I know. But yeah, so if you see it something like this, your model should be able to still detect it. And that's what we worked on. The idea is it's free form text condition detection. So you no longer, just restrict yourself to a set of object classes. You can detect anything that you describe in free form text. So how does this work? So if you compare the previous, the thing which was going up in the infographic earlier, this is what the output of that model looks like. They basically detect everything that you could possibly, find in this image. And then the multimodal model has like the hard task of figuring out which ones are actually useful. Whereas on the right, like this is what, if the text prompt was a blonde boy wearing blue shorts, a black surfboard, this is precisely what like our model would give us output. And then if you have some like downstream question answering or whatever, you can like use that. Or like if the question was like, what color shorts is the blonde boy wearing, for example, it would basically give you a box around the blonde boy and the shorts. So just the stuff that you need. I have 15 minutes.
You have however long you want, and however long the students are willing to stay. Yes.
Okay, so to explain our approach, you need to know what is Detector. So just as I had described what faster Rcnn is, this is another model which was proposed last year to do object detection. So faster Rcnn has like all of these non-differentiable components, which makes it hard to train end to end when you want to like plug it into some downstream multimodal application. But now, suppose you have an image, you have CNN feature extractor, just like in faster Rcnn. You get some image features. I say set because there's no sequence ordering in the image. And there's a transformer encoder decoder. So the processing is all done just using a regular transformer. There's no like ROI pooling, there's no anchors, there's no like hand engineered components which make it hard for your like the person designing or using it to like actually get all this stuff working. And then the output of this model is directly a set of box prediction. Now this will give you as many boxes as there are objects in the image. There's no like oversampling. There's like the ideal case, right? Like there shouldn't be any because there's like no explicit non-maximal suppression. The model itself has to kind of learn to do this like not deduplication of object boxes. So how it works in detail is given an image, the CNN predicts a set of image features. And like I said, because there's like no ordering till now, you also add like some positional embeddings, which are 2-dimensional. So that, because you have X and Y coordinates, so for each pixel, it needs to know where it came from. And then you just feed it, you flatten it. So you add the positional embedding, flatten the thing, and then you just feed it to a transformer encoder. At the output, you have the same length. Now, I think the key idea, there's 2 key ideas. One is like this idea of object queries, or which has now become like in the vision community called slot-based approach for this kind of detector. So essentially what it is you just have a set of learnable embeddings. These are initialized from scratch, and they're usually an upper bound on the number of objects that you want to detect in the image. So at the output, for each of these object queries, you're going to have like one MLP, which is basically going to predict the class, and one for predicting the box, like the actual bounding box. And if this particular embedding does not correspond to an object, like you can see here, there's just 2, right? So if there are some other queries, which obviously there will be because you always give 100 or some fixed number as input, then the remaining will say no object. So the difference, like to remind you compared to the other approach, is now you directly get a bunch of boxes, which actually tells you how many things are in the image, which helps with like the whole counting issue also, which we had before. Okay, so that was Detector, and based on that, we proposed MDeter, which is, so I'm going to explain now. So there's this cat, which is jumping over a fence. The image goes through a CNN, and the text, which is the associated caption for this image, goes through Roberta. And so at the output, you basically have a linear to project it down to like the same size, right? So in practice, we use 256. Also for Roberta embedding is bigger, it's like 768. So you also project this down to the same size to 256. And then you concatenate both of these on the sequence dimension. So that means it's like this flattened representation of this image will be like, batch size by some sequence length by embedding dimension. And then on the sequence dimension, the second dimension, basically you're going to add the text features, right? So both of these things go together as input to this encoder-decoder architecture. Sorry, I'm going to go back here to show you. This part is common to both of us, right? So, yeah, the output of this encoder-decoder is a set of boxes, just like before, like the queries which are decoded into boxes. But the main difference in the 2 approaches is that we no longer predict a fixed class label, because that's what we were trying to avoid, right? Like we don't want to be bound by a fixed set of object detection classes that we can like be predefined to like only be able to detect. So what we now do is for a given box, we have to predict the distribution over the tokens in the caption. So suppose this orange box has decided that it's going to be like box around cat. It needs to predict a uniform distribution over all tokens in the sentence, which correspond to the word, like to the words a cat, basically. So if there was, if the cat was referenced to again in the sentence, it would be uniform over that span as well as the other span wherever it's referenced. So it's like a many to many mapping. So yeah, there's 4 white paws. Each one of these will be aligned to like white paws. And for the one which is like no object, just like in Detector, we need a way to handle when there's more queries than actual objects in the image. So that's going to have like this dummy token in the end, which is like a no object. So yeah. So the loss I was describing just now is this is what it looks like in a toy version. So for cat, you will have like uniform like 0.5 over a cat. For white paws, it will be the same but over those words, etc. And for a yellow tree, it will be like 0.3 or whatever, or all those things. And it's trained using like a soft cross entropy loss. We found better results using focal loss and stuff, but yeah, if you're interested, you can talk to me. That's the first loss. And what this teaches you is positional information, right? It tells you like this query is like aligned to this particular part of the sequence, but it doesn't really tell you anything about the actual contents of the the word embeddings at that position, because you don't need to like actually know the word embeddings to be able to like predict this distribution. So what we're trying to do in the second loss is deal with that. So yeah, so this matrix over here is what is used to like actually tell you which are the positives and negatives, just like we had in Clip, if you remember. They had like the diagonal elements to be all positive, whereas the off diagonal were negative, because they were doing it like at the instance level, which means like just at the image and caption level. But now we're going to look inside the image. So suppose you have these three bounding boxes. So you have this red one here, which is around the blue ball, yellow cylinder inside this light green, and dark green for this whatever golden shiny ball. So the idea is if you have each of these tokens, ball or yellow, and these four predicted boxes, you have an X when the token corresponds to that box. So for the first token, it's ball. So yes, this one is a ball. So the red one is an X, as well as the dark green one. Whereas for the dark green ball, it is a ball and is also yellow. Does that make sense? So yeah, so you use the same kind of loss, the contrastive loss as in Clip, to align these embeddings. If you're interested in the equations, I didn't put them here, they're in the paper. So let's just look at some results. So suppose you have this image here, and you're given this sentence: one small boy climbing a pole with the help of another boy on the ground. And the task here, if you remember what place grounding was, is to return a bounding box around each of the places. So what our model predicts here, you can see, is like, yeah, the three basic, like the three phases which are involved in this image. On the right side, like you can see, a man in a white t-shirt does a trick with a bronze-colored yo-yo. Like, a bronze-colored yo-yo is not one of like the COBO classes or like PG class or whatever we train on, but like it can still figure out what these are, because word embeddings are powerful, and you use the word representations of like free-form text to like find what's in your image. It gives you a lot more power than predefined class labels. So yeah, we also get pretty interpretable predictions. Like if you have the question, what is on the table, it gives you a bounding box around what and around table, because it knows this is like a noun or like a phrase that you're interested in, and it predicts the answer laptop. Similarly, it's like, what color is the train? It puts a bounding box on the train and it says red. So it's like giving the answers for the right reasons. A lot of like models in the past have been shown to like give answers, but then when you actually query them and see where their attention is, it's on like some random part. And this is dangerous, because when you like have adversarial attacks on these kind of images, you don't want changes in like the background to affect your answer, or like in irrelevant things to affect your answer. So it's nice that we have like more interpretability. Just some like more examples from our collab, which you can play with if you're interested. It's on the website. It is like more free form stuff like orange shirt, flowery top. You can find these things. And the more interesting one on this slide is the one on the right, which has a car and an electricity box. Mainly because these are like the non-salient objects in this image, like it's somewhere in the background and you can still find it. So that's pretty cool that it can manage that. So yeah, so the key takeaways from this work was to remove dependence on pre-trained object detectors. So we're no longer restricted by fixed vocabulary. That was what we were trying to avoid. So now we can detect anything that is referred to in free-form text, like pink elephant or whatever, flowery top and things like that. And it also gives us interpretable prediction. So that was about our work. And now like the last couple of slides, just want to talk about some challenges for multimodal models. So the one on the bottom shows you the first challenge, which is hallucinations. Very often in image captioning models, they like depend on language priors. Like there is a table with a plate and a fork or a spoon. No, but it's going to be something random, but you're not going to look at the image because it's more likely according to your language model to say like this thing which is more common. So similarly over here it says a cat sitting on top of a laptop computer, very common, but not what's happening in this image. And then the second problem is gender biases. So apparently a lot of these models take cues from like I was saying, the background or like some weird context from the image to give the prediction instead of actually looking at the person in question. So this paper by Lisa and Hendricks basically says, you should make the predictions for the right reasons, like by actually having the attention map on the person. So they designed like something they call like Equalizer Models, so that if there's not enough information in the image, you're uniform over all categories of the whatever, what is the word for in fairness, like, you want protected class, I guess. Yeah, so.
But if you don't know the word, you can't really ask for the word, right?
Oh, that's for you.
But then, yeah, protected classes or properties, yeah.
Yeah, so things which, you don't want your model to be like, be wrong about, or like, racist or whatever else in this space. So like, so you want it to be uniform over this attribute, whereas if you have access to like information in the image to make that prediction, then it should be focusing on the right part. So that's what they do. And then finer grained understanding is something just shown on the top right, which is like word-based information, like a person sings at a concert and a man jumping into a river. You can see that there's river in both and there's men, I guess, in both. But there's like, the jumping or whatever, kayaking is like a very like finer grained attribute, which is really hard skill for our models to do today, especially for words. They're pretty good at like nouns, but verbs are really bad. And then the last challenge is what I mentioned earlier, which is like the precision that our models have right now is like really inadequate for real world applications, like for visually impaired people. So that could be a very important challenge to also solve. And finally, like some important research directions, which I think are important, but I'm just suggesting if you're looking for things to explore. So I think interpretability and explainability is like really important, because if we want to like make people depend on these kind of models for their everyday living, they need to know that they can trust it. So having explanations also makes models more robust, because you can tell if it's like giving an answer for a bad reason. Like, suppose, is there a red apple on the table and it says no? You don't know why it's saying it's no, but it says no, there is a green apple on the table. So then you're like, okay, it really knows what it's saying and I can trust this answer. So that's a really good direction. Few short task generalization. So currently, like, people are really interested in building generalized representation learning techniques, which I think is really a good idea, because we don't have that much task specific data, but we have like self-supervised techniques, and like all of these generalized representation learning techniques are coming up because you want to like have one system which can quickly learn to solve many tasks. And that's already like happened pretty much in NLP. If you see T5 and like all of these really big language models where you just say, do this task and it like translates or does whatever else. So we want to have something similar to that even in this space. That would be interesting. And then recognizing and reasoning over text and images is like super useful. We already talked about that. Also about red concepts, and weekly self-supervised training is what I just said. And then finally is like most of the stuff I showed you today, or all of it has been in English. There's other languages out there which people should be really working on, and extending multimodal models to multilingual contexts is like really important. Finally, I just want to say that this field is like really like hot right now. Like, I think that's an understatement, because like I stalk Twitter for what new papers are out there. I'm like, oh, okay, they did that too, cool. But like it's like really crazy how fast-paced this field is. Just this 1 week, like last week, there were these 4 papers by the same group that came out, and it was like they're all like high. They're all each breaking the benchmark on their data sets that they report on. Some even report on the same. It's like crazy. You just type on paper now. But yeah, it's pretty crazy that it's like so important to so many people, and I can see why, right? Like even for companies like Google, who are interested in search, for example, multimodal search is like pretty much the way to go forward, because like you can explain what you want in like as an image, as a text, or like, take a video of what you want. There's like so many ways to express yourself, and that's like pretty much the feature. Or there's some stuff like, suppose you want to order a dress and you're like, I describe what it looks like, and the model like returns a picture to me, and then you say, no, but like I want shorter sleeves or like whatever. So like image editing kind of thing. There's so many like interesting applications for this space that, that's why everybody's really, really excited about it. And that's why I am too. And hopefully you are too after today. So yeah, that's it. Thank you.
Well, thank you very much for a great talk, Aishwarya. Is there any, I don't know, one or two questions that you want to ask? But of course, as you know, Aishwarya is a PhD student at NYU, so you can look her email up very easily on the context. So if you have any further questions, you can always reach out to her by email. This is the time we actually did spend the entire lecture. So I guess we should just wrap it up here. But Aishwarya, again, thank you. And we are going to come back next week here for all the remaining lab sessions. They're going to work as if they are office hours, most of which are going to be over Zoom. So if you have questions, do come to the lab sessions, ask the TAs. But if you don't have any questions, you don't have to come to them. All right, sounds good. Have a nice evening, and I'll see you all next week. Hi, we can do it. Shut down. Yes.
In it.